All right, so we are going to do a little bit with motion equations now and relating them to our motion graphs. Let's start with an acceleration versus time graph, and let's make an assumption with this graph, one that you have to make when you're using your motion equations, which is that our acceleration is constant. With that assumption in hand, we can set up an equation that relates acceleration to velocity. Like we said in the last graph, or last video, the change in our velocity is equal to our acceleration times our time. So if I took one of these little areas here, I could figure out how much my velocity changes by. That means that I could break up this term. Delta V is the same thing as V minus V naught, still equal to AT. And then I could add V naught to each side, and that gives us an interesting equation that I hope looks familiar. That's our first kinematic equation. Cool, so we're one down, two to go. Let's go to our second graph here, and let's just build from this to the next one. From this acceleration graph, we could draw a velocity versus time graph that looks like this. Notice that it has a positive slope of 1, just like which is predicted by our acceleration with a value of 1. But that's not actually the only velocity graph we could draw. This one is just as valid as the first one that I drew, because it still has the slope that our acceleration predicts. And since we don't know anything about our initial velocity, either of these dotted lines are equally valid. So hold on to that thought, because we're going to come back to that. And we're just going to start looking and trying to create kind of a specific formula that we'll try to generalize. So the formula that I want to write is I want to write something like what I wrote here and write delta x is equal to v times t. But here's the problem. I was fine using a in this one because acceleration was constant. I'm not okay doing it here because v is not a constant value. V is a changing value. So that's unfortunate. I can't just write it like that. What I have to do or should do instead is say, well, what if it was the average average velocity? Then this would work because then I would turn this from being a triangle into like a nice flat rectangle that has the exact same area, and we'd be just fine. So let's get an average. I'm going to pick that point and this point here. And again, I'm choosing two specific points, and I'll show you why this works for every scenario in just a minute. But for now, let's just pick those 2 points because it's convenient, and we'll call this one right here our V naught, and this one up here our V, and we'll say V plus V naught all over 2. That's the definition of an average times t. I've just replaced that V with an average velocity, and it's still equal to delta x. Okay, this is lovely. This is off to just a wonderful start. And instead of using v plus v naught, though, why don't I try to do something something clever? And I will write this as let's plug this equation right here into there. And if we plug that in, we already have a velocity value. So we can say v naught plus at all over 2 plus another v naught. So this right here just replaced v for us, and we have the v naught. All of that times t is equal to delta x. Then I can just start simplifying this a little bit. That would be 2v naught plus, let's see, at, all of this times t, all of this over 2 equals delta x. Okay, let's keep simplifying it. Let's distribute that t into here, and that becomes 2v naught times t plus a times t squared all over 2. All right, let's pull this factor of 2 out, and we'll turn it into v naught t. Hey, this is starting to look like a thing, times 1/2 at squared. And all of that equals delta x. So delta x plus v naught t plus 1/2 at squared. And delta x is really the same thing as x minus x naught. So why don't I add an x naught to both sides, and I get x equals x naught plus v naught t plus 1/2 at squared. Ha, that was cool. So with that in hand, we now have our second kinematic equation. Our third kinematic equation, what we've already mentioned is that it's kind of convenient to have one that doesn't involve time. So I'm going to use my first kinematic equation, and I'm going to rewrite it. I'm going to rewrite it in terms of time. So I'm going to take it from v equals v naught plus at and write it like so. All over a, equals t. And from there, I can plug this whole equation into this giant monster of an equation. So by doing that, I'm going to say x, that's going into this equation here, x equals x naught plus v naught, but I have to replace v naught with these t terms. So it's going to be v minus v naught over a times t plus 1/2 a, and then v minus v naught over a squared. So this is going to turn into a beast, and I'm kind of running out of space. So I think what I'm going to have to do is I'm going to rewrite it all up here a little bit neater, hopefully. V naught, v minus v naught over a. Oh, there shouldn't be a t there. That was the whole purpose of what we just did. Plus 1/2 a times v minus v naught over a squared. All right, and with that done, now I can kind of get rid of this part, hopefully, and then I'll do the solving below it. Okay, so back to work. I'm going to change to blue, though. Blue is a nice color. This becomes x naught plus this. I'm going to distribute the v naught, so it's v naught v over a minus v naught squared, because I distribute it over a, plus 1/2. I'm going to distribute the a into here. Actually, I guess I have to square it first. Gross. When I square a value like this, squaring the top, that would be v squared minus 2 v naughts plus v naught squared all over a squared. Ooh, lovely. Now I can go to the next step. Let's see, nothing to do with the x naught, nothing to do with these right now, nothing to do with this yet. But now I can distribute the a in the half. So I'm going to distribute that a in the half, and I'm also going to start breaking these up into separate terms. No, I'll do that in the next step. Let's just say, let's put it all over 2a squared instead, so the half goes in there. But I'm also putting an a into every single term, so that actually gets rid of the squared term. Let's erase that. So I got rid of the a's there. I moved the 2 inside, and so I can just say v squared minus 2v v naught plus v naught squared. And then the last thing is I'm going to break these up into separate terms, and then I'm going to start canceling some stuff and cleaning up this giant mess. This is all equal to x. V naught v over a minus v naught squared over a. And then this would be plus v squared over 2a minus, this would be 2v v naught over 2a, but I could just write it as v naught over a, and then plus v naught squared over 2a. Lovely. If you're looking at it and starting to notice some things, yeah, we can probably get rid of or simplify some terms. I have a v naught v a here and a minus v naught v there, so I can get rid of that term entirely. How very, very convenient. And then I have a minus v naught squared over a and a v naught squared over 2a. So I'm going to actually just rewrite this as 2v naught over squared over 2a, which is mathematically the same thing. And that lets me simplify it a little bit because negative 2v naught squared over 2a plus v naught squared over 2a just becomes a positive v naught squared over 2a plus v squared over 2a. So these, I've gotten rid of those terms by combining them. I just brought that one down. I'm going to pull that x over. So it's x minus x naught equals all of these things. And then I'm going to multiply both sides by 2a. If I multiply both sides by 2a, I get something that looks like that. And now I just have v naught squared plus 2v. And boy, wouldn't it be convenient if I just, I'm sorry, this should have actually been negative from that step before. How convenient. Add v naught to both sides. V naught plus 2a x minus x naught equals v squared. And here is our third kinematic equation. All of these kinematic equations just came from our motion graphs and our understanding of motion graphs. And you may have noticed that the algebra here was pretty involved and pretty awful. And that's because, well, algebra is kind of awful. But the takeaway here that I hope you take with you is the motion graphs are actually easier to use than these equations are if you can get away with them. So I suggest that you very often try to sketch your motion graphs and see if what you can figure out with the motion graphs rather than trying to always default to the equations. Even though they feel more mathy, physics is more about learning to use the right tool than always using the fanciest tool possible. So that is the proofs for all three of those equations, and it's kind of our last connection that shows how all of these things we've been learning so far all relate to each other. So thanks for watching, and if you're wondering what the whole point of those proofs were, I suggest you work on them if you feel like your algebra is kind of weak. If you can do these three proofs, you're pretty much set for all of the math that you're going to be asked to do in this particular unit. So do these proofs over and over again, trying not to look at my work, but just kind of trying to figure it out on your own. And if you can get from start to finish, from equation 1 all the way to equation 3 with your own work, then you're totally set on the math parts of the physics. And then we can start making sure that we're working on the physics parts. So thanks for watching and have a great evening.